Hi again. We're here for part 3, video 3 of this week's lectures. This is a short one, but it really represents a lot of things converging together. I hope it'll be clear. I think it'll be clear. Let's be optimistic. But of course, I look forward to discussing it with you and hearing your questions about what it's all about, because we're going to move from the arguably sort of boring world of resting potentials that we covered last video in the context of a membrane, of an electrically active membrane, and move into the domain of what's called action potentials. And like they sound, action potentials mean something happens. They're a dynamic process. Before we get into that, or to start our discussion really in that, I want to show you this functional diagram of an ion channel pore. It says a working hypothesis for a channel is the label on this. And it really describes a schematic diagram, like we've been looking at in lots of different contexts, of a bilipid layer with an embedded protein. So both those blobs belong to the same protein. It wraps around in 3 dimensions and creates an opening in the middle called the aqueous pore. You've seen pictures like, well, not quite like this, but the same functional idea. There we had proteins obviously folding back and forth. In this context, we've turned those proteins into blobs, and to even highlight more clearly the functional aspects that we want to capture here. And what we also see in these blobs, in these functional behavior of the membrane, is a thing called a sensor. And a sensor senses things, of course. It measures something, or at least responds to some influence. In this case, it responds to the voltage that exists across the membrane, or the electric field that's generated across that protein embedded in the membrane. There are also selectivity filters. So we've mentioned several times that ion channels are selective for particular ions. We have a sodium ion channel, potassium ion channel, calcium ion channels. We talked about chloride. And the selectivity varies with the actual channel type, but most of them have some kind of selectivity. And then they also have gates, or at least one gate. Some have 2 gates. And these gates open and close. And you can easily anticipate that this combination of a sensor that drives a gate, which opens and closes, is going to add some potential for dynamic behavior. And that's how to think about these ion channels and how they behave and how they generate an action potential. So that's the functional sort of physiology diagram. This is literally out of a physiology book, of course. And it already gives you a clue of the kind of behavior we're trying to capture. Now, the trick that we're going to use here is to say, we're going to take that additional behavior and add it to our same circuit that we had before for the static situation, and just modify the circuit a little bit to make it describe this behavior. And it turns out that the circuit looks just like the one we've seen before, except it has a couple of new arrows. All right, so what are the arrows? The arrows indicate that the resistances, in this case the potassium and the sodium resistance, are variable. Now they're variable as functions of voltage, hence the sensor that senses voltage and controls the gate. And they're sensitive, or they're functions also of time. And that means that they will open and close based on some kind of weird internal clock that we don't actually fully understand. So the gate may open under voltage stimulus, and it may close just because time runs out. Like a screen door. You kick it open, and over time, it slams shut. And that timing of the slamming is a function of features of the door, how squeaky the hinges are, whatever. So it's a similar or analogous behavior here with these ion channels that are capable of opening their gates and closing them again. So that's the transition to the circuit world. Now we have a representation that we could arguably feel comfortable with, because we've seen a representation like this before. We've analyzed one in the context of the resting potential. All that's changed is the resistance has changed. So we can, in principle, take any resistance conditions that we know about, any resistance values that somebody gives us from an experiment or some other prediction, and we can plug those into the circuit, solve the circuit again, and come up with answers. So what does this look like, let's say in a practical case? So let's take the simple practical case of the sodium channel opening. So what does that mean? It means the sodium channel resistance drops. And you see, if you look at the table here, we've added another column. We have the resistance of those channels at rest. And you see here for sodium, it's 30 kilo ohms. and then the resistance when the channel opens. And you see how dramatically it drops. This is enormous. This is orders of magnitude. A drop down to 0.0083 kilo ohms, or I guess 8.3 ohms. A tiny resistance compared to the 30 kilo ohms we had before. So, and this is very realistic. These are realistic numbers. So now we say, okay, what's the effect of that change going to be? Now, in terms of solving the circuit, I'm not going to repeat it because we've done it before. We've come up with an equation. We've come up with a voltage, membrane voltage estimation or calculation that we can just apply to this scenario again. And I've just plugged it there. You see the equation that we had before, the membrane voltage being the sum of the sodium equilibrium potential, the difference between the potassium and the sodium potentials, and this ratio made up of the resistances of the two important resistors at play here. And we can plug the numbers in as we did before for the resting situation, and we get minus 67 millivolts. That's the resting potential we saw before, very close to the potassium equilibrium potential, which we see from the table is minus 78 millivolts. But now in the open channel situation, the open sodium channel situation, we have a massive difference in the sodium resistance, a massive drop in the sodium resistance. And that changes the scenario quite dramatically to give us a value of 55.6 millivolts, almost the same as the sodium resting potential. So we've gone from the equilibrium potential of potassium all the way up to a value almost equal to equilibrium potential for sodium. And that shows the effect of these resistances in how the circuit behaves. The intuition for this will come with time, but this is how it should feel. It should be that one or the other dominates depending on which resistance is lower or which conductance is higher, because then that arm of the circuit, that ion channel, dominates the behavior, and the membrane channel follows that behavior of the ion channel. But we have the proof here. We have the numerical proof here that this is how it works. Now, we also solved this circuit in the context of the Thevenin equivalent with an attached capacitance, and the capacitance stays the same whether at rest or during an action potential. That's this value of 1 microfarad per square centimeter. And so we can keep that value the same and figure out the time constant. So now let's look at what happens during the time constant change. We see that equation that we got before. We had a resting Thevenin equivalent resistance that we figured out to be 1.4 kilo ohm. Obviously that changes dramatically when we reduce the sodium resistance, and all of a sudden our Thevenin resistance is 8 ohms or 8.25 ohms here. Of course, with that our time constant changes equally dramatically from 1.4 milliseconds to 8.25 microseconds. So 3 orders of magnitude difference in the time constant. That means that the behavior of the membrane has changed dramatically. Its whole time to respond or time to change has really shifted by orders of magnitude. It suddenly becomes a much faster system, and it's able to respond more quickly. The voltage is able to change more quickly. All those sorts of things that we associate with a small time constant. So now we can say, well, great. I can replace this circuit with a Thevenin equivalent. Got all that figured out. I can attach a capacitance to it. Looks like a simple RC circuit. I know how to solve for RC circuits, exponential function, time constants, all that good stuff. And you can get some distance with that sort of thinking, but the question then becomes, is that really the whole story? Is it really as simple as saying, I have some kind of step function in the resistance, that the resistance of the sodium channel changes dramatically, and then I get a responding exponential rise in the voltage that it achieves from this small value, minus 56 to plus 55. So do we get that sort of change in an exponential fashion? And that's the action potential I've been talking about? Well, unfortunately, it's not quite that simple. And it's not that simple for a couple of reasons. So let's have a look here. So here we see an action potential. This is the behavior we're ultimately having to replicate. We see this is a very rapid behavior. This is the red curve. It plays out over 2 milliseconds, very quickly. And it has initial value, has a rapid rising phase, a peak value, then it goes down again, even to a slightly lower voltage than it started, and then gradually creeps back up to that original resting voltage that we talked about before. So how do we explain all that? Well, the sodium resistance changes, as we've just described, and that drives the membrane potential to be more positive, to go from this strong negative value to a much more positive value. And that's what we see. The red curve tells us that indeed the membrane voltage goes from this minus 50 something up to a plus 50 something in a very short time, very rapidly. Very rapidly because we have a short time constant. However, the resistance of the sodium channel doesn't stay constant for very long, doesn't stay low for very long. Instead, and here we have it expressed as conductivities, it rapidly reaches a peak and then goes back down again. Well, why does that happen? Well, it happens because of the time dependence. These resistances depend on the membrane voltage to open their gates, but then time to close their gates. So the sodium channel opens very rapidly, allows current to flow through very easily, but then it closes down, like the screen door slams. And at that point when it slams, that channel closes. Now we see a second curve, that's the green curve. That's the potassium. We haven't talked about that yet, but the potassium has its own dynamics. It has its own opening characteristics. At a certain voltage and with a certain time dependence, it too will open. Its conductivity will also go up. And if we open that, it changes the circuit again. And we'd have to recalculate the circuit. In fact, for every one of these time points, we would have a resistance for sodium and a resistance for potassium. And we'd have to recalculate what the membrane voltage will be at that point in time. And then also take into account the fact that we have this capacitance, which of course will change the response. It will change the behavior, if you will. So all those things added together are what give us the action potential. And so to simulate that, to write down equations for that, it's still very possible. And that's been done, of course. It's the formulation that led to a Nobel Prize in the late 50s. So it's not that old knowledge. But we are able to capture that behavior, quantify that behavior, and describe it in very quantitative terms. So we're able to describe, as you see here, the conductivity, for example, of sodium as a function here. There's m to the 3 and all this stuff is just kind of details, but the main part is you see there's an m function, an h function. They both depend on voltage and time, and if you add them up together, you get a description of that rapid rise in that blue curve going back down again as a function of the voltage in red above it and time along the x-axis. So you can see it's complex. There's no question it's complex. But ultimately, it's not that complex in the sense that at any point in time, if I know these values, if I can predict what the conductivity is of sodium and potassium, then you have all the knowledge you need to determine what the membrane voltage is. And this allows you to already imagine how you might be able to, in a way that's similar to the Euler's simplification, or the Euler's numerical method that we use to predict the mechanical behavior of the heart, you could use a similar numerical technique here. In fact, you could use exactly the same numerical technique here, and you could describe that action potential. You could write a program that would implement this action potential and replicate this behavior that we also see in the measurements that biologists and scientists do of these membrane potentials as functions of time and voltage. So with that, hopefully you can see we've closed the loop, right? In this one short lecture, I've been able to bring into you all sorts of the things you learned in mechanics, the time constants, the RC circuits, the Euler's equation, the electric circuits, the Thevenin equivalence, and the biology of a membrane and the functional behavior of something as strange and amazing as an ion channel, all into one package. So all the concepts that we've been thinking about this whole semester really come together here, and I hope they provide you with a conceptual framework that you can then build on, that you can then move into physiology courses, courses in biomechanics, courses that follow up on what we've talked about here, and use this material, deepen it, refine it, but still building on these same concepts, these same key, core, important concepts that will not really change. We'll just build on them, add sophistication, and use them to solve some fabulous and fascinating problems that we have in biomedical engineering. So with that, I'm going to end this lecture and the series of lectures that I did in the context of the material for this course. I hope you've enjoyed them. I've enjoyed your feedback. I've enjoyed listening to your questions and helping you to understand these concepts. I hope the rest of the year, the rest of this semester goes well, we get through this, and I look forward to seeing you all in the future and wish you the best of success in the biomedical engineering program and in all your future endeavors and careers. And I look forward to seeing all of you again soon. Thanks so much.